Recall Cayley's theorem. G is a finite group. Then we can embed G as a subgroup of a symmetric group on n letters, S sub n, where n is equal to the order of the group. Because of this, we want a better understanding of the symmetric groups. We'll also define a new class of groups called the alternating groups. Now, for the definition of S sub n, recall, we'll let X be the set of labels 1 through n. An element of S sub n is just going to be a bijection from X back into itself. We'll call the elements of S sub n permutations. Now, if we let n be equal to 6, okay, I'll pick a bijection as so 1 to 1 onto. It's more convenient to represent our bijection in cycle notation. So what do we do here? I'm just going to pick any element, so say 1. I see that 1 goes to 5, so I'm just going to list where each element goes to, going from the left to the right. So I have 1 goes to 5, 5 goes to 6, 6 goes to 4, and then 4 goes back to 1, and then I'm going to close this up in parentheses. Now I haven't used everything, so I pick one that we haven't used yet, say 2, 2 goes to 3, 3 goes to 2, and then I close it up, and I notice that I've used 1 through 6, so I'm done. That tells me everything I need to know about this bijection. Also note 2 other items. If the cycles are disjoint, meaning they have no labels in common, we could just push them past each other to get the same bijection. Also, we can shift our cycles either to the left or right as long as we wrap around, and we don't change the part of the permutation affected by this cycle. So this is the same as 5, 6, 4, 1, 6, 4, 1, 5, 4, 1, 5, 6. And 2, 3 is the same as 3, 2. Now, for the multiplication, we have functions, so we're just going to use composition of functions. Okay, now this is a little confusing. Here, we read from left to right, but when we compose functions, okay, when we put an actual element in here, we're going to go from right to left. So for instance, if we take sigma 1 equal to 1, 2, 3, sigma 2 equal to 2, 4, 5, and say we're in S sub 5, when I take the product, what do? Well, we're going to have, okay, sigma 2 first, so we're going to have 1 goes to 1. Then when I get to sigma 1, 1 goes to 2. So we have 1 going to 2 in the product. You can work out the rest of these. And we get the bijection by just taking, okay, 1, 2, 3, 4, 5 goes to 2, 4, 1, 5, 3. And then decode. To understand permutations, we have the following 2 propositions. First, every permutation can be written as a product of mutually disjoint cycles. Then, every permutation can be written as a product of 2 cycles, not necessarily mutually disjoint. We also call 2 cycles transpositions. So what our second proposition says is that we can think of the 2 cycles as the atoms of the symmetric group. So we can write every permutation as products of those atoms. Now, for the first proposition, I want to fix a permutation S sub n. I want to put a partition on the set X of labels 1 through n. If we consider the subsets in the partition, so we pick one, that'll give us a cycle. And then if we take all contributing cycles, we get a representation of our permutation in cycle notation. Now, if I want a partition, I need an equivalence relation. So I'll say 2 labels I and j in X are related if and only if j can be written as an integral power of our permutation on I. Note here we're using sigma to the 0 equal to the identity element. Now, to see that we have an equivalence relation, we need to show reflexive, symmetric, and transitive. Those are straightforward, so I leave them to you. Once we have the equivalence relation, we form equivalence classes, and then we get a partition of our set X. Now, another way to phrase all of this is in the language of group actions. So if we take subgroup generated by our permutation in S sub n, call that H, we'll have a group action of H on our set X. That gives us a partition of X into orbits. To each equivalence class, we attach a cycle. So we'll fix a class E sub I. We get a cycle by sending I to sigma I under sigma. Sigma I goes to sigma squared I under sigma, and so on. Because S sub n is finite order, our list is going to end when we get to sigma to its order less 1 applied to I. When we apply it one more time, we get the identity on I, which is just I. So it's going to bring us back to the beginning of the list. That means we have an unbroken cycle, and the elements that appear in the cycle are going to be precisely those that are in E sub I. Now, if you check your relation, you might wonder, well, what if j is equal to sigma to a negative power applied to I? Because sigma has finite order, we could add multiples of the order to L, and we'll eventually get that to be a positive number that's between 0 and the order of sigma. So that's going to be some number in our list. Now, that's going to produce, okay, because the EIs are disjoint, the cycles that come out will be disjoint. Because we have a partition, every element of X is going to appear in one of our cycles. So that completely describes our permutation as a product of mutually disjoint cycles. Now, for proposition 2, we can take proposition 1 and apply the following recipe. So if I have the cycle A, B, C all the way up through D, this can be written as, okay, we're going to go in reverse order. The 2 cycle AD, we go all the way down until I get to the 2 cycle AC, 2 cycle AB. So let's check this. First, I have A goes to B. B doesn't appear in any of these, so we have A goes to B. B is going to go to A goes to C, and then C doesn't appear in any of these, so we have B goes to C. Till we get to the end of the list, and then I want to know where D goes. D doesn't appear until we get to this 2 cycle, and then we have D goes to A, closing up our cycle. So, proposition 2 holds. Now, an application of proposition 1 is to count the number of elements in S sub n. So we know the order of S sub n is n factorial. Okay, that's the number of bijections from a set with n elements back to itself. By our proposition 1, we can label all those elements by their cycle structure. So for instance, if I want to understand, okay, the number of elements of a given cycle structure, okay, I can list the cycle structures, and then we have the following recipe. So the number of cycles of length k, we take n factorial, divide by n minus k factorial, and then divide by k. So the idea is if I have a cycle, well, when I write it down one way, I'm going to have other ways just by shifting the elements. So 1, 2, 3 is the same as 2, 3, 1 is the same as 3, 1, 2. Now, we just do the count straightforward though. So for instance, if I'm in S4, the number of 2 cycles, I have 4 choices times 3 choices. Divide by 2 because we can switch. So I get 6. For 3 cycles, we have 4, 3, 2. Divide by 3, I get 8. For 4 cycles, we have 4, 3, 2, 1. Divide by 4, I get 6. Then for the product of disjoint 2 cycles, it's a little tricky. We have 4, 3, 2, 1. I could do a switch here, so I divide by 2. Here we divide by 2, and then we can interchange to divide by 2 again. So we take 4 factorial divide by 8, which gives us 3. Now, if we add, we get 24, which is 4 factorial as expected. For S5, okay, we know how to do the cycles. We know how to do the product of disjoint 2 cycles. When I do a product of a disjoint 3 cycle with a 2 cycle, what are we going to do? Here I have 5, 4, 3, 2, 1, so 5 factorial. We divide by 3, We divide by 2, but there's no switch, so we stop there. So I divide by 6 to get 20. Again, we add. This adds up to 120, and that's equal to 5 factorial, checking our work. As an application of proposition 2, we can define the sine function on S sub n. Sine is going to carry S sub n into the group plus minus 1 under multiplication. We can define sine recursively as follows. So sine of the identity is 1. Sine of any 2 cycle is minus 1. And then we extend by the product rule for sine. So sine of a product of permutations is equal to the product of their sines. And then we can apply proposition 2. Now, what this gets us, the sine of a permutation is equal to plus 1. If we could write the permutation as an even product of 2 cycles, minus 1 if we can write it as an odd product. The only catch here, we don't know that the sine of a permutation will be independent of the factorization into 2 cycles that we use. Now, we're not going to show that here, but we will note we can define sine completely independent of this using linear algebra, but of course we would want to link back to this realization also. Now, we have that sine as a homomorphism. So if we take an even product times an even product, we have an even product. Even times odd is odd times odd is even. Since we have a homomorphism, we could look at the kernel. So the kernel of sine, okay, that's going to consist of all even products of 2 cycles, okay, even permutations. We call this subgroup of Sn A sub n. Because it's a kernel, it's going to be normal in S sub n. By our isomorphism theorem, we have the S sub n mod A sub n, the quotient group, is isomorphic to plus minus 1. So that means A sub n has n factorial over 2 elements. Okay, again, normal because it has index 2. Now, big theorem is going to be that A sub n is simple when n is greater than or equal to 5. So recall that means there are no normal subgroups in A sub n except for the identity and A sub n itself. We'll show later at least for A sub 5. Let's apply our counting method to some alternating groups. First, we have A4. This should be familiar. This is the rigid motions of a regular tetrahedron. We have the identity. There's one of those. We have 3 cycles. This is something to be aware of. We have an odd number of labels in a cycle giving us an even permutation. The number here, we have 4, 3, 2. We divide by 3, we get 8. Then we have products of disjoint 2 cycles. So 4, 3, 2, 1, I divide by 8, we get 3. This adds up to 12. That's 24 divided by 2, and 24 is 4 factorial. So that checks out. Note A4 is not simple. We have the normal subgroup given by the identity and the products of disjoint 2 cycles. So you should check that this is at least a subgroup. For A5, same idea. We have the identity, we have 3 cycles, we have products of disjoint 2 cycles, and we also have 5 cycles. And again, note an odd number of labels in a cycle gives an even permutation. We do our counts. We get 60, which is 120 divided by 2. 120 is 5 factorial, so that checks also. Now, if we think of the 2 cycles as being the atoms of S sub n, the atoms for A sub n are going to be the 3 cycles. So we have every even permutation can be written as a product of 3 cycles, if n is greater than or equal to 3. So in A5, we have 3 cycles, products of disjoint 2 cycles, and 5 cycles. So what's the recipe for our last 2 items? They're given as follows. So let's check the first one. I have A goes to B goes to C, so A goes to C, B goes to D, then D goes to D, so B goes to D. D goes to A goes to B, so that closes this cycle up. Then C goes to A, closing this cycle up. So that checks out. I'll leave it to you to check the case for the 5 cycle. But the way we should interpret this one, if you note, what we're doing is we're taking the last 2 labels, pulling them off into their own 3 cycle. So you'll note we could keep applying this to pull off 2 labels at a time. So this is good for reducing our long cycles to shorter ones. Now, let's show the proposition. So we're going to use induction on the A sub n that our permutation lies in. So for our base case, we have n equals 3. So for A3, we have the identity and 2 3 cycles. So our proposition holds in that case. If we suppose it's true for A sub n, then if I have some permutation in A sub n plus 1, I check and see if there are any fixed labels. If we have a fixed label, then our permutation actually lives in some A sub n, okay, for a given set of labels. And then we can just use the induction hypothesis and it's true. If there's no fixed label, okay, we break it into cases. If we have all 2 cycles, then we could use 1 to get a 3 cycle to appear. Then I multiply by the inverse of the 3 cycle. We've taken a label out, and then we apply our induction hypothesis to what's left over. Then we put our 3 cycle back in, and it's true. If we have a cycle with length greater than 2, then we could use part 2 here. The idea, I could pull off the last 2 labels. We get a 3 cycle. We multiply by the inverse. What's left over has fewer labels. So we apply the induction hypothesis, and then we put our 3 cycle back in. So it'll be true in that case also. One way to phrase our proposition, AN is generated by the 3 cycles. Let's use this to give our first proof that A5 is simple. We'll have a second proof, much easier, but we need to know more about conjugation. Now, for the first part, suppose we have a normal subgroup in A5. If N contains a 3 cycle, it must be all of A5. We'll see later on that this is true in general. Now, we need the conjugation rule, which we showed in the A4 video. So, what this says, if we take some permutation, conjugate by another permutation, the rule is to just apply sigma to each of your labels. And that's going to be your new permutation. So the cycle structure stays the same. Now, if we have a 3 cycle in our normal subgroup, then all of its conjugates must be in that normal subgroup by normal. So we're going to have all possible relabelings of 1, 2, 3 using even permutations. So that's the catch. We have to use even permutations since we're in the alternating group. Now, I'll leave it to you to show, by brute force, that we'll get all 23 cycles. We'll have a clever way to show this later on, but for now, it's just a computation. That means I have all of our 3 cycles, and they're going to generate an A5. Now, with that, to show that A5 is simple, we just need to show if we have a normal subgroup that has more than the identity element, it has to have a 3 cycle. So what are the possibilities? Well, the elements in A5, we have the identity element, we have 3 cycles, we have products of disjoint 2 cycles, and we have 5 cycles. So I'll be clever about the way I choose my elements. Now, let's suppose we have a product of disjoint 2 cycles, call it 1, 2, 3, 4. I'm going to conjugate this by the product of disjoint 2 cycles, 1, 2, 4, 5. And when I do that, what's going to happen? The 1, 2s are going to pass through and just cancel out to leave me with a 1, 2. If I conjugate by 4, 5, well, that's going to send 4 to 5, 5 to 4, which just means we're going to send 3, 4 to 3, 5. Now, we have a subgroup, so when I multiply, what happens? We take 1, 2, 3, 4 times 1, 2, 3, 5, I get the 3 cycle 3, 5, 4. That means we have all of A5. If instead I have a 5 cycle, okay, I'm going to conjugate by 2, 3, 4, 5, assuming we're using 1, 2, 3, 4, 5 here. That's going to send me to 1, 3, 2, 5, 4. We multiply, and that gives us the 3 cycle 1, 4, 2. That gives all of A5. So we see the A5 is simple. Okay, there's no normal subgroups except for the identity and the group itself.